In this session, we are going to explain. We are going to discuss about the source and reverse algorithm. Uh, so I'm going to cover the introduction to quantum computing, source, and we are going to discuss about what is source algorithm, how to implement, and what is the algorithm behind that. And we are also going to discuss about the reverse and the implementation part and the conclusion of what these two algorithms is going to create an impact on the quantum computing. So first thing, I hope that in our previous session you have discussed about the what is the classical computer, how the quantum computers was evolved, all those things. I'm just going to give a little recap on this. So it is with a no doubt the classical computers have powered the modern world. So all the complex problems are faced with the help of zeros and ones. So, but however, these problems, when the problem size grows, like a cryptography, optimization, and simulation problems, the classical computers find the limitations. So, on that cases only, our quantum was now into an apart. So, this is going to be in a new computing paradigm where it's going to use the principles of quantum mechanics so that with the help of this quantum mechanics, all the critical problems, all the limitations where the classical problems is suffering, that can be overcome with the help of quantum computing. So this can be done with the help of the quantum mechanics. So this is responsible to make that problem to exponentially faster than the classical machine. So that only we are evolving to this new quantum paradigm. So I wish to discuss on one second. So, before going into an source and groovers, we need to check with a few basic terminologies of quantum. One is qubit, superposition, and entanglement. The first one is a qubit. We all knows the classical computer is a fundamental of zeros and ones. As like that, qubit is nothing but a quantum bit. Is that a fundamental unit of quantum computing, which is very similar to a classical bit. So as we have told, the classical bit is zeros and ones. So we can tell the qubits as to be 0, 1, or both at the same time. So this comes to an next what is it interesting topic known to be in a superposition, where the power of qubit really relies on this part only, where the qubit can be placed. That is, what is the difference between a classical and the qubit now? So classical also represents zeros and ones. Qubit also represents zeros and ones. But classicals represents one at a time. But in case of qubit, both the state, that is, a multiple states can be represented at a time. So this is possible with the help of a superposition. So that is the power of a qubit. This makes a quantum computer to be work as faster than the classical computer. That is, we can able to represents the multiple state at once. So this makes a quantum computer to be exponentially more powerful. So we can see here in our slide. I hope you all can see that. So the two qubits. We can represent a 4 value one at a time, but with the help of a superposition state, I can able to state 4 values at once. And 10 qubits, 1024 values one at a time, but all at once in a superposition we can able to place. When I come with a 50 qubit, it become a 1 trillion. It all at once I can able to represent. So with the help of superposition, we can able to represent the multiple state at once. So that is the power of the quantum bits. That is the power of the quantum computing. So with the help of the superposition only, we are just doing the parallel computation. So with the help of parallel computation only, quantum computing computes the process much faster than the classical computers. So the next one is next basic terminology here we can coin to be an entanglement. So entanglement is whenever we have two or more qubits, when it was strongly linked, so automatically changing of one state will automatically updated on the another. For example, we can tell the entanglement examples to be enough. For example, in case if I twin the dices, okay, that you can consider that entangled qubit as to be in a twin dice. Okay, so if you roll a two classical dice, their value are independent. It will be some, so one die will give 6 and one dice will give us 7, 3 or 1, whatever may be. But whenever we are, when we are twin the dice, that is called to be an entangled qubit. If the dice are entangled, rolling one die as 6 could means the other instantly shows the 6. That is, even across, even the dice or across the galaxy, it will be changed to the twin dice. For example, if one dice is showing 6, automatically other dice will also show 6. So this makes a computation more and more powerful, and it also makes to be a more faster. The next important thing here we are just going to see about the inference. So this is a part which is very much needed for the Brewer's algorithm. So I have included in this as a terminology. So here the quantum computers, with the help of the terminology called interference, it just cancel the wrong answer and boost the correct one, so that we can during the probability we can get to the correct answer rather than the wrong answer. So you can able to understand this interference with the help of a noise cancelling headphones. Nowadays we have a noise cancelling headphones, right? So for example, whenever we use a headphone, the classical computers will check every answer by one after another. But when we goes with a quantum computer, with the help of this inference, you can enhance the correct answer. For example, noise cancelling headphones removes the unwanted sound, like that. This inference removes the wrong answers, and it will, with the help of the probability, it will give with an right answer. So that this inference is very, very important. So we are going to use this inference in then a search problem. That is, in case of Brewer's algorithm, for amplifying the probability to correct the search result, which is not available in the classical method. So that this method, using of this inference, makes the Brewer's algorithm works faster than the classical method. And the next thing, I hope you all knows about the common quantum gates, that is Hadamard gate. So this Hadamard gate will use to create a superposition. So the best example is flipping of coins. In case if we are using in a classical bits, a coin will be flipped. Either we can get a head or in a tail part. But when we use in a Hadamard gate, it will flips on the superposition one. That is, spinning of the coin can be on both the state. That is 0, 1, and all at once until we can measure it. And the next one is known to be in a C0 gate. It is known to be in a controlled and not, which is used to create an entanglement. So for example, if a one qubit flips, automatically, instantly, the another qubit will get into updated. That can be achieved with the help of the gate called to be in a C0 gate. And the next one is in a Pauli gates. So this can be applicable on instead of an X gate. That is, it is nothing but a classical flip gate. It's nothing but it's need to be an X gate. That is, it's known to be in a quantum knot. And next one is a Toffoli gate. It is nothing but that it's a version of a classical AND gate. So by knowing this, all these terminologies, the next question in our mind, we need to get, why can a qubit perform better than the classical computing? That is, how the qubit can able to do the better performance on the classical computing. On the cases, we already saw that the classical bit and the difference between the qubit. A classical bit will be on processing the information using a bits on zeros and ones. For example, each bit will be like a lighting of switch. Either it will be resides on 0 or it will resides on 1. But the power of quantum computing relies on the superposition, where it has zeros, ones, and also it resides on the same time. That is, it can be state on the same state also. That is known to be in a superposition. Here you can able to see, we can able to see the problem here. where imagine you have a lock with 4 dials. Each dial can be of 0 or 1. Okay, so we can have the combination of 0. That is, we can have the 16 combination, right? Yes, we can have the 16 combination over here. So a classical computer will try to do this each combination one by one, and it takes a 16 steps in the worst cases. It will take a 16 step at worst cases. But in case of quantum, with the use of a superposition, that is, superposition means a single qubit can represent both zeros and ones. On that cases, the 4 qubit can represent all the 16 state at the time. All the 16 state. So what it does happen, it does not store 16 classical values, but rather than 16 complex probability amplitude to can be set at the single state itself. That is, at the single phase on the same time itself, it can able to set it off. So for each basic state, from we can tell that from ket of 4 zeros to ket of 4 ones, this can be associated with a complex number that is called to be an amplitude that may be determined with a probability. So 4 qubit, we can take into the probability of alpha of 0 to ket of 4 zeros plus alpha of 1 ket of 0001 till A15, sorry, alpha 15, we can take it to be a ket of 111. So all alpha zeros and alpha 1, alpha 15 will act as in a probability amplitude as in a complex numbers. This probability will make a 16 complex aptitude. So first of all, we need to understand why we need of a 16 complex aptitude. So since each qubit can be of 0 or 1, so 4 qubit can be has a 2 to the power of 4, that is 16 possible classical state. However, as like in a classical system, this stores only one state at a time, as I have told already, and I also mentioned here. But in case of quantum system, with the help of a superposition, we can able to store the 16 states simultaneously. So this make that state to be run simultaneously. We have already told that with the help of a superposition, we can make a parallel execution. So with the help of that nature, we are making the 16 states simultaneously, which have its own complex probability amplitude. So this is how the superposition makes it to be more faster. So instead of checking a 16 combination one by one, a quantum computers possess them in a simultaneous manner, so that the time taken by computing will be reduced, and it makes to be in a much faster than the classical one. So the next one is visualizing the power of superposition. So for example, if you have three classical bits, if we are talking about a three classical bit, they can only store one at a time. For example, as per the previous example, I'm just showing that we can have a combination of 000, 001 and 0101 at a time. But if you have a 3 qubit, as I have already told, with the help of superposition, we can store all these combination from 000 to 111 same at a time. So more qubit will increase the power of a computational power. So you can also see here 1 qubit, 2 state at once, 2 qubit, it is in a 4, 3 qubit, it is in an 8 state, followed by 10, it is in 1024. That is 2 to the power n. N is nothing but the qubits. So this makes a superposition to be a more powerful one. And the next one is entanglement. So as we have already seen what is meant by entanglement, entanglements make us to communicate, make the qubit to be communicate instantly. We no need to bother about how far the distance was, even it was far away from the galaxy, we can able to communicate with the help of the entanglement. So normally when we approach with a classical approach, if you want two classical bit to share the information, we need to send the data between them. But when we have the quantum approach, the two qubits are entangled each other, where even though if it is in a light years apart, it can able to change it. So for example, as I have already told, when the two twin dice was, when we are playing a twin dice, when one dice is giving an a 6, automatically another dice will also reflect a 6. So that is the nature of the entanglement. So the quantum computer can coordinate the computation among the multiple qubits instantly and allow us to solve the problem exponentially faster. So with this, the superposition and entanglement is responsible for the fastest execution, and superposition is responsible to storing the complex amplitudes, and the entanglement is also responsible for the exponentially faster. So I hope everyone knows nowadays the real world application is moving on within a quantum, where we can break the encryptions. We are just on the way to do it, and we are just drug discovery, and with the help of an AI, we have come up with a protein fold. We are coming within a protein fold, and we are identifying the diseases with the help of a DNA changes and all those things, so that it was a very much added for the drug discovery also. Similarly, when the AI combined with a quantum, it also makes the enormous changes on the drug discovery that will be in a allow us to create a new medicines that will become faster to our market. And combining the quantum computing with an AI and machine learning, where we can able to process the vast amount of data. So that is also is feasible over there, and we also can come up to optimize some problems which is not done by the classical computers over the year. So this is the quick recap about the quantum computers, where first of all, we need to have the clear understanding of what is the difference between the classical and quantum, and how the quantum become more powerful with the help of a superposition entanglement. These are the two things which we needed more. And the next thing we are going to step in on Shor's algorithm. Excuse. Yeah. So as you know, source was first developed by Peter Source. Is a quantum algorithm which is going to effectively factoring the large number in the polynomial time. Even though we have some algorithm which was achieved within a sub-polynomial, source is achieving the execution with the polynomial time. So we know the effective encryption technique called to be an RSA, which was relies on the factoring of number into the prime component. So since it was an assumption that till today, no classical computers is ready to factor this large number. But when we come the source algorithm along with the quantum mechanics, that is quantum mechanic property, like a superposition, inference, entanglement, automatically this source encryptions can be broken out. So this can be done in an exponential time, that is in a polynomial time, we can able to do it. So before going to understand how the source algorithm is executing, we need to first understand what is the difficulty of factoring the large number into their prime component. So this is the very much we need to get into understand of it. So I'm just going into the first understanding what is known to be in a factoring of it. Consider I'm just giving a two bucket of paint. One is on red, one is on blue. Now I'm just asking you to shade on the purple. Then it will not be a very difficult work to you, right? So you will be mixing of colors and you will be coming off purple color. But when you started with a purple, if I'm asking the question, I'm just having a purple. I'm just asking you what are the colors I can combine together to create a purple color. If that is a question, it will be a much more difficult to you. So this kind of problem is called to be a trapdoor problem, where one way of calculation is very easy. For example, calculating the 163 into 149, I can be getting of 24,287. If I'm giving an answer to you and I need to find what will be the product, what will be the multiplication of it, doing the reverse of this will be quite difficult over here. So on this case, think about instead of thinking about a paint, you just think about the number as I have told already. If you are having a large prime, that is 163 into 149. When I need to calculate it, it was very easy. I can easily multiply those two numbers and I can give the product of those numbers. In case if reverse the question, for example, I'm just giving the 24,287 to you and I ask you to reverse the operation. This is known to be a prime factorization. So this is where it relies on. This is called to be a prime factorization. So this is an underpins of the encryption where RSA works. That is, with this combination, they are creating a public key. Okay. So once in 1991, the RSA laboratory was conducted one cash reward competition. They have asked to find the prime factor, two prime factor for the smallest number which you are looking on the screen now. So when this competition was launched, the RSA 100, for example, 100 decimal numbers, few of the people have given the solution on 1991. And for the 250 digit long, some of the people have given for on the 2000 years of it. So it takes a longer duration to answering for the RSA factoring challenges with the help of a classical computer. So the traditional computer, it is nothing but the classical computer to crack RSA, that is prime factorizing a number will be harder for a traditional computer or a classical computer where when the digits is growing. For example, you can see here for the 100 we can able to is when it was in a 250 digit, automatically you can able to see that all the purple color is known to be in a few days of the launching of the RSA vehicle results. So it takes a longer time to calculate the prime factor of the number of digits when it was very longer. But when we go for a prime factorization of a source, it is no longer, that is, we are not going to have too many years with the help of a prime factorization where source, with the help of a source algorithm, we can able to identify within a minimal hours or within a minimal years itself. So this is the breaking point of an RSA. So this makes, for example, you can able to see that I'm just giving one number where we need to find the prime factor of it. It may take 1 to 2 years to factor that. But it was shown that with the help of a source algorithm, to make this factorization can be done in a minute or it can be in hours. So what do you think that if the RSA was breaked on the classical computer, what is the next thing? That is the enhancement of the cybersecurity is needed now. So this makes a significant move on the cybersecurity challenges, where we are moving to an urgent need to prepare the post quantum era. So this leads to an post cryptography researchers and all those things. So this is the main part of the source. I hope that you have understood what is the prime factorization and how it was difficult for the classical computer to have the factorizations and how the quantum computer can able to evaluate this. So once you need to implement the source, the prerequisite is the first one is a mathematical prerequisite. The first one is known to be a modular arithmetic. As everyone knows, mod, that is we need to have the remainder when it was divided by n. So the example, for example, I have given the example as 10 mod 3 is 1 because you all knows that 3 into 3 is 9. When I add plus 1, it gives 10. So I have divided as 1. And the next one is a greatest common divisor. So we will be following the Euclidean algorithm to compute the GCD of two number. So key factor is if GCD of A and N is greater than 1, A is a factor of N in a trivial cases. So sometimes we will be considered the non-trivial cases also. And next one is an Euler-Toylen function. This is going to count the digits from 1 to n, that going to be in a co-prime of n. And the next one is, this is in a very important thing that is called to be in a period finding. So whenever this is in a very important part in a source algorithm also. For example, for an integer a that is in a co-prime to r n, the order of n should be in a smallest such that a of n of one mod of n. That is, you can understand from the example that a is equal to 2, n is equal to 15. We can tell the R is 4 because it have the period. See here, 1, 2, 3, 4. Till it reaches 1, it acquires the period of to be in a 1. That is called to be in a period. And with the help of a continued fractionals and rational approximation, we will be applying the quantum Fourier transformation to extract this R whenever we going into a circuiter. So we will be using the continued fraction and rational approximation to have the best rational approximation algorithm. So we need to move on this. And the next one is quantum prerequisite. So whenever we come with a quantum prerequisite, we need of qubits superposition, and we need of an Hadamard gate, controlled U gate, and the quantum Fourier transformer. So Hadamard gate is used to for the create an equal superposition. Controlled U gate will be used for the modular exponential, and quantum Fourier is used for extracting the periodicity. This is known to be in a periodicity. What I have told, order of the integer, where I need to extract this, I need to compute the iteration from 2 to the power 1 to 2 to the power 4. So I need to have this exponential, extracting the periodicity with the help of a quantum Fourier transform. So whenever we have a quantum phase estimation, so we will be using an eigenvalues for an unitary operators to determine the period of R also. So as of C now, we will be seeing of all these things with the forward of we can go with an understanding. These are the prerequisites which is essential for the source algorithm. Now we can see how this algorithm is working. So the first one is we can see why the integer factorization is hard. We need to first understand. As we already discussed, why it was hard, how the classical computer phase is to be an art, how the quantum computer with the help of a superposition and entanglement, it was achieving that. It is quite difficult for the classical computer to make a factoring for the large number. That is a main issue on the classical cryptography. So for example, if n is n equal to p into q, that is if n was given for as a public key, when it was need to be a decoder, where I need to find the factorization of p and q, where p and q need to be a prime. So no classical computer can able to execute this with the help of a polynomial time. So the best classical algorithm which was did is known to be in a general number fleet leaves. This was done within a sub-exponential time. But in contrast, the source can able to achieve with the help of a polynomial time. So that we are just moving for a source algorithm. So as we saw some mathematical prerequisite and quantum, so here I have given the step-by-step where we can able to achieve the source algorithm with the help of a mathematical foundation, where we are just going to factor an integer which can be reduced to finding the period. So first, what is the steps first we need to follow is, we need to convert the factorization to a period finding problem. So for that, first we need to do, what is the first step? Suppose we want to factor in, we need to choose some random integer from 1 to n. And we need to compute the GCD of that particular number and the random integer. So if it happen, if we have already found the factor, if we have already found, otherwise you need to continue it. So once you found the factor, automatically you need to apply it with a power x mod of n. What is this a power x mod of n? This is nothing but a power x mod of n. It is used to find the order of the integers. So we just find the order of integers. That is a periodic. It means that how many interval of time which we are going to take to find the mod of it. We are just going to find it. For example, if the period is going to be even, on that cases, we just going to do the a power r by 2 plus or minus 1 mod of n. This is the one thing. That is, we are just going to compute GCD of a power r by 2 minus 1, and also we are going to give a plus 1 in order to get a non-trivial factor. What is meant by non-trivial factor? For example, if I'm just making a going to find the prime factor of 15. Sometimes the trivial factor is 1 and 15 is also can be taken, because the number which was divisible by itself should not be taken. So I'm just considering it to be a non-trivial factor. So non-trivial factor, in sense, we can consider 3 and 5 as a prime factor. So to consider the non-trivial factor, we are just considering this particular formula, that is a GCD of a r by 2 minus 1 and also the plus 1. And next one, we are just finding the quantum Fourier transformer to find the R over here. So we are just using the step 2. And the next one is, we are just going to set the quantum circuit for the source algorithm. So whenever we have a quantum circuit, the first thing we need to have a 2 register. The first register to set the superpositions of an input value, and the second register to show the function. For example, the first register to n, where for the large number, 2 times the bit of the length of n will need to be there. And second register, 2 qubits will, in order to store the mod values, we will be having the second register. For example, n is equal to 15, we will be using an 8 qubit into it. So with the help of an Hadamard gate, so we will be have the equal position. That is, we will be setting the equal superpositions to perform the Hadamard gate. So this will help us to maintain the uniform superposition in all possible x values. It will take all the states and it will maintain the uniform superposition in all possible x states. So it will be considered within a second register. So whenever we are just working on the second register, we will be applying the unitary transformation to compute it. So with the help of a unitary transformation, we will be having we need to have an entanglement of the 2 register. And the second registers will always use to check with a value of AX mod n. And the first register will collapse for this superposition of the state, where it need to have the same periodicity. So applying the quantum on this portion, we can able to measure the given value proportional to 1 by r, so that it can able to determine the R value over here. So this can be done. So after that, we need to do the classical post processing. For example, if after doing all those things, once we are finding the periodic with the help of an quantum Fourier transform, setting of the entanglement and the Hadamard gate, all those things, if the periodic is even, as I have told already, to compute a non-trivial values, I'm just going for a GCD of AR by 2 minus and plus to have a non-trivial. In case if R is odd, I just need to take a different A and I need to repeat it again and again. So this is the process will goes until I get an even number. Okay. So that with the help of this with the help of this one D, the source algorithm is achieving the log n of q. So this makes a checking of the factors. That is to a number, to a key. When we are trying to find the prime factors, automatically this makes a polynomial time, and it makes to be an checking of the factor will be an efficient manner. Okay. So what I have told already, I have given in a step by step. So as just in a refreshing point, you need to choose a random register from A. You need to check on a GCD. If it is already factor, I need to use a quantum computer to find a period where I need to set the superposition. Then I need to compute the quantum gate and I need to apply the quantum Fourier transformer and I need to measure R. Now I will get an R in the third step. If R is even, I will compute the GCD. Otherwise, I need to pick another number, another A, and I need to move with again I need to come with step number 2. So this we can done with an, I'm just going to show an example that is called to be a prime factor n is equal to 50. So you can choose a random number as an integer a. So when we choose an integer a, that is I can able to choose a random number from 1 to 15. So on that cases, for example, I'm just trying to pick a to be a 7 over here. So now I'm just going to compute GCD of 7 and 15. This is equal to 1. So I'm just going to proceed it. If it is not, I'm just going to select another number. Okay. So defining the function ax mod 50. So a is nothing but 7. So I'm just giving in a 7 mod 50. Now I'm just going to compute. That is, I'm just going to change the x to be 1, 2, 3, and 4. Okay. So I'm just going to check with 7, 1 mod of 15. It gives 7 and its square, it become 49, 49 mod of 15, it become 4. So till x4, I'm just going on. So now we can see that the function is periodic within a period called r is equal to 4. So what is the next step? So in this step 2 and step 3, continuation of step 3 only, we are just going to design these steps with the help of an quantum computer where we are going to set the superposition and entanglement, and we also going to apply the quantum Fourier transform to do this. So once it was done, automatically we are going to check whether R is even. So once if it is even, we are going to proceed with, as I have told already, I need to compute a GCD, right? So GCD we are just computing. Now we are getting 48. Now again 48 by 15, I'm just getting 3. Similarly, as I computed for minus, I need to compute for a plus also. So if R is even, I need to compute for GCD a power of R by 2 minus 1 comma n. And also I can proceed with a power of R by 2 plus 1 comma n. So these two things I need to do here. So what is the reason to compute both things? To avoid the trivial cases. That is non-trivial values I need to come up. So that is the number which is divisible by itself should not be comes. For example, 1 and 15 should not come as a prime factor. So we are considering this formula to compute it. So once we done, we successfully got the factor, that is 3 and 5 for the prime factor of 50. So as it is very similar, we have considered only 15 to be factor. Think about the large number like n is equal to 2048-bit RSA key. So this is not possible for in manual computations or in a classical computer. So we need of a quantum computer along with a quantum Fourier transform to efficiently to find a f. And we need to think that again, if the f is not an even, again this computations need to be processed on. So this need to be this is only feasible with the help of a quantum computer. So I hope everyone have understood what is the process behind the source algorithm. Now we can see the implementations of these source. So I just share my implementation screen. So to implement, what are the steps? I hope everyone can able to recall those steps. So the first thing is to have the implementation of a source, I'm just using a Colab, and I also imported the QSkits with this Colabs. So to have it, I'm just import the files, and I have some setup. So like an NumPy, I have used for the numerical operation, and I have from the math, I have imported the GCD. This is used for the from the math module. I'm just used it to check on factors, and QSkit, it is used for build and stimulate the quantum circuit, and air simulator, it is going to provide a backend to run one quantum circuit simulations, and fraction, this is going to help me to measure the phases into a rational approximation. This is going to find the what is that, the period which we have told, right? That is R, which is going to find by this fraction. So the next thing is I have defined it one function. That function is nothing but a quantum Fourier transform. So this is going to used, I have used the functions to get the output in then a reverse order compared to a desired basics, that is swapping the qubits. This can be done with the help of an first for loop, that is this can be done. And we also for each for loop that and I also defined it the controlled phase, that is the rotation of an Hadamard and the Hadamard gates. So for each qubit j, for each qubit j, the inner loop of applies the control phase. This going to apply the inner control phase gate, that is known to be in a CP. So this going to be applied with the help of 2 into j minus k for every qubit. So after these rotation, the Hadamard H, that is we have defined it here, the Hadamard H, that is the Hadamard gate, will be applied to the qubit j. So this sequential implementation will be the inverse of a quantum Fourier, which is essential for reading out the phase information that encodes the period of function. What is the period of function? That is f of x is equal to a power x mod of n. So this part will help to read out the phase information that was encoded from the period function. So I have used this method over here. And the next one, I have used the modular exponential. So where here we just realize the purpose of a source. So the first thing is the goal of this particular function is to build the unitary operators. So this is the unitary operators which is going to show the maps, going to map the ket of x, that is a ket of x1 to the a of x mod of that is I can tell to be a, I'm just ket of, we can tell the ket of x that need to be denoting to be an a x mod of n. So this here we are just going to simplify with, in order to make an mapping of ket 1 to a to the power of x mod of n, we are just making a simplify with the help of it. So this is going to give a control qubit. So this is going to have a control qubit where from the counter register, the function going to compute the power power a to the power 2 control, that is mod n. So this is going to result, this result is going to convert the binary string of length equal to the number of targeted qubit. So with instead of going with the representations of an ket 1 to the a power x mod of n, we are just making the with the help of this power formula, that is power a 2 to the power control mod of n, we are just going to convert the binary string length equal to the number of targeted qubit. So for each bit in the binary representation, reading the least significant to most significant. So if the bit is 1, a C0 gate is applied within a control qubit, controlling the correspondent targeted qubit. So a barrier is applied here. So this, with the help of the barrier, it has added a visual representation to set the operations in the circuit. So here we need to see one important thing here. That is the real source algorithm. Whenever we use in a modular exponential, unitary is much more complicated. So this version is quite simplified within a high level of simulation, but a real working of a source on the modular exponential, the unitary will be in a quite complicated over there. So the next one is I'm just including the function for the factor verification. So this is a factor verification which I wish to do for a non-trivial factor. As I have already told, this function going to found the factor or non-trivial. That is, it should not be 1 and or n itself. For example, if it is a 15, it should not be 15 or it should not be 1. And their products equal to 1 also. So this particular steps will ensure that the algorithms should not reflect within a trivial solution. So I am expecting for an other than 1 and the n part. And the next part is to find the classical period finding. That is, we are just used to find the going to find the period. That is a period of a mod n for verification over here. That is, we are just going to use this as a helper function to find this particular part. That is a power to x mod of n. This is going to work it on. So iteratively, this going to check for the powers from a until ar. So it's going to check from 1 and it going till a to the power r mod n, that is going to be 1. So it's going to search for a fallback if the quantum part of the algorithm does not yield the Z. For example, if R is not in a range, it will go within a fallback and it will search for the next thing. And the next function is for a source. So we have just tried to implement the source with the help of all calling of the previous method, which we have defined it here. So primary check is, the first primary check I wish to do here is, I need to check whether the n is even. Okay, the factor is trivially, it is 2. If a common factor, if I'm going to find the GCD of a and n, that should not equal to n, sorry, it's not equal to 1, then a shares a factor with n. That the factor is written immediately. No issues, it will be written. So the next one is we are trying to calculate the count of it. So we use a count equal to 2 into we are just we are just going with it. So we use an n count to count the 2 into log base 2 of n qubit. We are just performing with the help of this particular line. So this is used to hold the register at the superposition state. So that after applying the inverse QFT, where we have applied it already, the QFT. So this is going to apply the inverse QFT, will give us an estimate of the phase which related to a period also. And we also defined it one targeted variable. That is, this is going to be in a register which we have initialized to be in a log base n qubit. So we have represented. So this targeted register is going to use to store the result of the modular exponential. As I have already told, when we are discussing within a quantum prerequisite, we have told about a 2 register, right? One to store in a superposition and another to store in a targeted register, that is in a modular exponential. So for that we have used this 2 register that is called to be an account and another thing to call to be a targeted over here. So one is used to store the superposition and another is used to store the modular exponential. So this is a thing. And next part is known to be a quantum circuit initialization, where we are just creating a quantum circuit. So we just making the targeted register and the counting register together to find the QC. That is, a quantum circuit is created where the addition of the 2 things, that is a counting register and the targeted register and the n count of the classical bit. That is, it is going to measure the counting register. The targeted register is it will be initialized to an normally, because it is typically done by an X gate at least of one significant qubit. And next one is we are just applying the Hadamard gate over here, because in order to create a superposition, we are just trying to apply the Hadamard gate. So each qubit in the counting register is put into a superposition with the help of the Hadamard gate here. So this is going to create an equal superposition over all possible values is over here. And the next thing, we are just going to apply the modular exponential. That is, for every qubit in the counting register, the modular exponential functions will be applicable. So each of this operation is known to be a controlled operation that multiplies the target register by a power n. That is, we are just going to stimulate a power 2 power I and mod of n. That is, I going to be counting of the qubit from the ket 1. So we are just going to work with that. And after doing this, we are just going to inverse the QFT. So I'm just calling the QFT, which was already, I have defined it here, right? So I'm just going to call the QFT. So yeah, after inversing the QFT. So what this part of QFT will do, that is the query of quantum Fourier transform. This will be applied on the counting register. This transformation converts the phase information into the form that can be read out by the measurement. So along with it, we will be having the measurement register is also measured. The resulting the binary string representations that also can find the period of R over here. So we will be using it. And also we will be using the simulations thing. And we also checking with once we have finded that trivial factor, that is, we have avoided the trivial factor. So fraction of phase method will be called and trivial factor will be avoided, and we will be checking whether it is an even factor as per the algorithm of an source. We will be checking of here. And if it is an even number, we will be going and finding the period that is known to be a non-trivial factor over here, so that we can able to find the GCD of x minus 1, and we also can find the x plus 1 over here. So after this, we are just calling the all those things, and we can, in case if it is not equal to 0, it will be calling again, and all the similar process will be goes again and again. So in order to test this, I'm just taken the same example for n is equal to 15 and 7. So when we compute this, we can able to find the factors and analyzing measurement and the phases, all those things, and we got the final result of the factor to be in a 15, that is 3 and 5. So since I hope everyone have understood this, if it did not, I will share the code so that you can have a quick refresh of this also. So one thing we need to keep in mind that we need to have an modular exponential quantum Fourier transform. Then we are just finding the period. In case of source, we are just setting the superposition, one circuit for superposition, another one circuit for an entire, targeted circuit, and targeted register, targeted register for a modular exponential. Then we are just finding we are calling the quantum Fourier transform to find the period R. And after finding the period R, we are going to check whether it is even or odd. If it is odd, the previous steps need to be continued again. If it is not, if it is an even number, you need to find the GCD of, that is, you need to find the factor 1 and factor 2 with the help of a GCD of x minus 1 and x plus 1. So this will give an non-trivial factors of the particular number. So with the help of this, we can able to find the prime factorizations of a number. So I hope that every people was understood about the source algorithm and the implementations of the source algorithm. So now I wish to switch to an PPT part. So the same code I was given here. To work this, you need to install the QSkit along with an QSkit AER. So as you all know, the QSkit was updated with an 1.0, the latest version. You need to use its imported files and dependencies based on the latest updations of an QSkit. So the same code I have given for the reference, I'm just skipping here since I have explained all these. So I'm just skipping here. So now we need to come with an main thing that how many qubits are needed for the source algorithm. So to first of all, before knowing about, before thinking about the how many number of qubit it needed, we need to think about the physical qubits and logical qubit. So what is mean by a physical qubit? It is nothing but a raw qubit. That is, it will be an error-prone qubit that will be currently available on the quantum computers. They are just working on the quantum computers. It is an error-prone one. But what is a logical qubit is, it is a fault-tolerant qubit. That is, it is used for the quantum error correction. So this can be in a group of physical qubit. For example, since today's quantum computers are noisy, that is, we are just using in a many physical qubit. So we need a more number of qubits to create one single logical qubit. For example, it need of 1,000 physical qubit that is needed to build a one logical qubit. So on this cases, I hope that we need few more years or not in a year, few more days to go to build within a logical qubit also. So for example, you can able to, I'm just given one qubit estimations of an source algorithm over here. For example, 2048-bit RSA key, based on the circuit design and optimization choice, we can have a 5K plus 1 logical qubit that is leading to a 10 million physical qubit as per in 1996. When it go with an 203, that is 2003, we need of 2n plus 3 logical qubit, which is going to be an 4 million physical qubit. In 2014, based on the proposal of these people, it can be of 9n plus 2 qubit, that is 80 million physical qubit, to reduce the circuit depth. It is not for the logical qubit, it is for the reduced depth. As I have already told, the cracking of this RSA key is not only feasible, not only based on the logical qubit, it is also based on the circuit design also. So they have come up with a proposed that 9n plus 2 qubit implementation is required for 18 billion of physical qubit to reduce the circular depth. And on 2021, they have come out with a 20,000 logical qubit, that is 20 million physical qubit that could break the RSA of 2048-bit in an 8 hours itself. They have come up with a proposal that with the help of 20,000 logical qubit, that is, it is equal to 20 million physical qubit. As I have already told that to make one logical bit, we need to have an enormous physical qubit. So they have come up with the Gidney and Ecker on 2021 was estimated that we need of 20,000 logical qubit that is responsible to crack down the 2048-bit RSA within 8 hours. So currently on 2020, only a few hundred physical qubit, we are just we are very far to break the modern cryptographic system. I hope that we can be achieved at this year end or maybe on the upcoming years based on the leading giants. They will be working on that. So at present, the source algorithm cannot be practically run on the real world cryptographic numbers, as we have seen some hardware limitations that we need of a logical bits, and we need to cut short the circuit design and all those things. So currently they have achieved the source algorithm for 21. This was achieved in 2012. And the smallest number, which we have factored now, that is a factor of 3 into 5, this also they have achieved that. So the normal challenging to running on the source algorithm is high qubit requirement, what we have seen, that is a logical qubit, and the noise and decoherence. That is, we need of an error prone due to the instability of an qubit. We need of a noise and decoherence. We need to overcome it. And circuit depth. Surely we need to overcome the circuit depth so that deep quantum circuit and increasing of error rate can be reduced, so that only they are working on it. So the researchers are working on the fault-tolerant quantum computers that makes a source algorithm to be an effective. And also the National Institute of Standard and Technology is actively developing within a post-quantum cryptography, and many of the researchers is working on the post-quantum cryptography. And as of now, we can say that RSA encryptions remain safe, but the advancement of the quantum computing is quite challenging for this. So we need to cross our hands for the quick updations of an source algorithm. So I hope that everyone have understood what is the source, why we need of what is the need of the quantum computer, why we need of a research on post quantum cryptography and the quantum cryptography, because of the RSA and the public key encryptions. All those things cannot be done but then a prime factorization of a classical. So we just it can be achieved with the help of a quantum computer. And how the source is executing, we have seen the mathematical prerequisite along with the quantum prerequisite, and also we have seen the algorithm and implementation. I hope everyone is okay with that. So the next algorithm we are just going to with an Groover's algorithm. 1 second, please. The next one is known to be a Groover's algorithm. So this algorithm is mainly for the quantum search. That is, in case of unsorted database, if we are searching for something, the classical searching algorithm, compared to a classical searching algorithm, this Groover's algorithm will be much faster. Okay, so this was invented by a Law Groover in 1996. This algorithm will provide a quadratic speed up when compared to a classical brute force search method. For example, if I'm trying to search an item in an unsorted database, it may be take off in a big order of n operation in a worst cases. That is, for example, if I have an 100 item, then I will be searching within 100. I need to do the 100 comparison of searching for an element. But in case of an Groover's algorithm, we can find with the help of an order of root of n, right? So this operation can be done with the help of a quantum superposition and the amplitude amplification. So these two things, along with an entanglement and interference, this Groover's can achieve this particular time complexity. So normally this Groover's algorithm can also used in a cryptography to break the symmetric encryption, optimizing the problem, machine learning, AI search problems, etc., etc. This applications can be used. So Groover's mainly works with two things. One is superposition. The next one is known to be an amplitude amplification. We all knows that what is meant by superposition. That is, we are just going to create a quantum state that going to represent all possible solution over here. And the next one is an amplitude amplification. This is going to increase the probability of correct answer. So here is what we just come with. We just need to recall the terminologies called to be an inference, right? So we have seen that inference, right? So that is the terminology. This is useful to perform the amplitude amplification. That is probability to increase the correct answer rather than the wrong one. Okay, so we need to, we just moving with that. Okay, and the next one, to know about the Groover's algorithm, before that we need to have some prerequisites on the Groover's, that is the fundamental quantum concepts. The first one is a qubit and superposition. So to achieve the superposition, we need to use a Hadamard gate. So is a fundamental unit of you always know that qubit is a fundamental unit, and Hadamard gate will apply on the qubit to have an equal superpositions. So and and we can able to have an multiple qubits. We also have an multiple qubits, that is Hadamard gate is able to create a multiple qubits on the all possible state, and all four state we have already discussed this, all four state exist simultaneously with an equal probability it will be achieved. So that only we have told that 2 to the power 4 is equal to 16. All possible four states will be available on the equal probability we have seen on the previous slides. So now we need to have a question why the superposition is very, very important in a groovers. So when we initialize all qubits in superposition so that all possible solution exist at once. So instead of searching at one state at a time, we can evaluate all state in a simultaneously or parallelly. Is it right? In case of classical, what we will do, we will take one particular thing and we will, as like in a linear search, we will be having of searching methodology, right? But in case of groovers, the superposition will help us to search simultaneously, that is evaluate all the state in parallelly instead of checking one state at a time. So that is how the superposition is helpful in the Groover's algorithm. So the next one is known to be an oracle function. This is a very, very important function in a Groover's, where this is going to make the correct solution, where we are just going to imply the inference over here. So this function is a quantum function which is used to identify the correct solution. Okay, this is going to act like a black box or a hidden box. Okay, so if we given an input, it tells us whether it is a solution, whether it is a solution by flipping its faces off. It will give the solution. So classically, we can go with a state by one by one. Excuse. As we already told, classically we will check each state one by one, but by in quantum we can check all state at once. So this can be done with the help of an oracle function. So this is a function that can be represented in f of x. This is going to return 1 if x is correct solution. If x is not a correct solution, this is going to give us a 0. So for example, we can able to understand this particular oracle function with suppose we are searching for an get 101, okay, as a correct solution. The oracle, this oracle function, what it will do is it applies the phase flip gate to the bit hit 101, flipping its sign. Okay, the state 101 is now out of the phases compared to other. Okay, so it remain unchanged. Okay, in case if it is a correct solution, it will give a solution. That is the thing. Okay, so it applies the phase flip. That is what I'm telling. This is going to apply the phase flip. Consider if I'm going to perform in a 3 qubit, that is a 101. This phase flip is going to apply on the correct solution. So it's going to flip the solution over here. All the remaining state will get to be an unchanged on this. So now we need to get into understand that why the oracle is important. Oracle function is important in the Groover's algorithm. So it marks the current state without revealing it explicitly, right? So that only we have called it to be in a black box or the hidden box, right? So it does not reveals it explicitly. Okay, only if the current state is available, it will be given. After marking, we're going to use an inference. What we have seen as a terminology, we are just going to use an inference to amplify its probability so that we will be getting the correct solution. Until we get in a correct solution, it get into amplify its probability. In case if it is wrong, it again amplifies its probability. So only the correct solutions will be given with the help of a phase flip. The wrong solution will never be shown so that it acts as in a black box and it amplifies its probability. So that only this oracle function is very, very important. So in this oracle function, this is going to act as a black box where our input is going to have a face flip to get the correct solution. So this correct solution on the face flip can be done with the help of an interference. That is, we are just going to amplify its probability. So this is going to be done over here. And the next one is known to be a diffusion operator. So this is what I have talking about. That is called to be an amplitude amplification. That is where interference going to be implication of it. So after applying the oracle, we just need to often a correct state can have the negative amplitude while other remains a positive. To increase the probability of measuring of in a correct state, the quantum operation called diffusion operator will be applied on the marked state. So this will make us to work with the Hadamard gate need to be applied and inversion of a mean operation. Applying the Hadamard gate again. Actually, first you need to apply the Hadamard gate to all the bit, and next thing you need to inverse about the mean operation, and you need to apply the Hadamard gate to apply again. Okay, so so this operation will be carried out. So once it's done, we can have you can able to see here. Start with an equal probability. We will be using an oracle flip to do the flips of the qubits, and diffusion operator will be done. That is amplifies 101 amplitude and decrease the others. So that this can be approached, this can be achieved with the help of an or of square and iterations, so that we can have an 100% of probability can be done. So the diffusion operator consists of following step, as I have told already. So the diffusion operator, that is applying the Hadamard gate, is very, very important. So what we will do to move back to the equal superposition. So whenever we apply the Hadamard gate, we will be achieving of an equal superposition, right? So when I applying the Hadamard gate to all qubit, I will be move back to the equal superposition on it. And the next one is applying an inversion about the mean operation. We neglect the deviation from the mean probability. And the next one is to apply the Hadamard gate on a H gate. This will make us to compute the basis. That is, convert the amplitude to a deviation from the mean. This is, we are just doing the converts to ambiguity. That is, this is going to compute the average amplitude at all stage, and we are just going to invert the amplitude of each state across the mean. That is, the correct state amplitude increase with other and decreases will be happen. And next one is repeat the Grover's iteration to get a square root of n. We are just going to have an iteration over here. So each iteration going to have the responsible to increase the probability of the current answer. That is what here a main thing. So each and every iteration is responsible to increase the probability of current answer rather than the wrong answer, because it was hidden by our black box. That is called to be an oracle box. So that is done. That can be done with the help of an oracle box. Okay. So these are the these are the prerequisites that need to be known for the Grover's algorithm. And the next thing, we are just going to see the step-by-step of Grover's algorithm. The first thing I need to set within a qubits, and the next thing I need to apply, as we already told, I need to create the Hadamard gate for all the qubit. For what? To set a superposition of all possible states. And the next one is known to be, I need to have an oracle function. What is the work of the oracle function? To phase flip it. Is it right? To phase flip the correct solution. In order to get a correct solution, we are just going to have an oracle function of it. This oracle function is going to encode the problems being solved. And we are just going to apply the Grover's diffusion operator with an oracle function. This is going to amplify the probability of the marked state and reduce the probability. Again, we are just applying the Hadamard to make the inverse about the mean function. We are just going to repeat the process. That is, oracle under the diffuse operator is going to applied approximately square root of n times, so that the probability will be getted in a correct solution rather than computing the wrong answer. So after required iteration, the qubit collapsed to the state to have the high probability. So for example, I hope that everyone have understood the algorithm part. So for example, if I try to have an unsorted database where I have an four items, that is A, B, and C, a classical search will goes for a linear search. For example, at a worst case, it will go for a linear search where it will have a four check. It will check for A, it will check for B, one by one it will check for C, and another it will check for D. But groove-wise, with the help of a superposition, it will be of root of 2. That is, within a 2-step, it can able to check on the unsorted database. So this can be done with the help of a superposition. So this superposition makes the quantum bits, that is a qubit, to represent all four items in a simultaneous. Oracle makes a correct item, that is it, with the help of a phase flip, it will be do. And amplitude amplification is responsible to give always the correct answer. And the measurement is used to for a high probability, that is checking within a high probability. That is a 2 steps is in a high probability over there. So this I have given only for the 4 item in the database. Consider if I'm having an 1 million of item in my database, the classical computer will always take a order of n, that is known to be an 1 million, while the groovers will be completed this steps approximately in 1,000 steps itself. So now I hope you have understood what is the power of Groover's algorithm on the quantum search rather than the classical search. So now we are just going to see the hands-on implementation of the groovers for a 3-qubit to find a marked state of ket of 101. So for that, I'm just have taken and imported the required libraries and dependencies. Just skipping to the collab.
Hello, Gayathiri ma'am.
Yeah, sir.
Yeah, can I ask one question, ma'am?
Yeah.
Yeah, in binary search, we know that log base 2.
Log
So,
n.
log
Log
n
n.
base 2. But in you said in the Gore algorithm, it's
Groovers.
root of n, isn't it?
Yeah, sir.
How it is possible, ma'am? If I have 4 values, root of 2 search, I can find out where the value is there.
Sir, in a groovers, they will be working with an qubit, right? For example, we are just achieving the superposition.
Okay.
That is, we are just finding the complex probability amplitude that can be achieved with the help of a superposition. That is a 2 to the power of, for example, if I'm taking as a 4, it will be considered to be a 4 qubit that can be able to store a 16 complex probability amplitude.
What is 16 complex probability means? What is the meaning of that?
Yeah. So, for example, each basic state, for example, consider that we can able to have a 16 combination, that is a ket of 4 zeros till I'm just computing to one triple one
Four
combination. Sorry, 4 ones. Okay.
4 ones.
So this can be considered as a complex number. So when I'm representing within a 4 qubit, all the complex aptitude, that is a 16 complex amplitudes, will be represented as possible on the classical state, that is 2 to the power 4, it will be represented.
That's fine,
That
man.
is 1
Now,
by
now you
4.
are telling that all the 16 values we can take in a particular time.
Yeah, and the same time.
At the
That is
same time, we can take.
amplitude.
Yeah, correct.
Yeah, amplitude
But
will
the
be
problem is
taken.
again that all 16 values we need to store somewhere else. Assume that.
That is why we have used the Hadamard gate to find the superposition of all the combination of the gates, sir.
Okay.
We're using the Hadamard gate to apply on the all possible bits.
Okay, madam.
So that is the first step we are just going.
Yes.
Yeah, thank you. Thank you, sir. So now we can see the Groover's implementation. What we have seen as an algorithm, we just make it to be an implementation. So the first thing, we just included the header files, that is an dependencies of it. So I have included the quantum circuit. This is used to create and manipulate the quantum circuit. And the next one is an AR simulator. As I have already told, it is used for the high performance quantum circuit simulator. This will be used from the QSKIT. And plot histogram, you always know to visualize the measurement result. And I have also used the transpile. It is going to optimize the circuit for execution on simulators or on the quantum hardwares. And as usual, we have used the NumPy. Okay. So the first thing I have defined it here is known to be an Groover oracle, that is known to be an oracle function. So this is an oracle function which works as like a black box, right? So this oracle marks that I have defined out here, this oracle mark, this is a solution which I have set it for then a ket of 101 by applying the phase flip operation. That is, I'm just going to have a multi-controller Z operation over here. Since this ket of 101 is in a solution, we just going to apply the multi-controller Z operation over here. So to do this, what is the first thing we have did here? We just applied the X gate. That is, I'm just going to flip the qubit ket of 101 into ket of 111, which makes a controller operation easier. Then we just applying the Hadamard gate. That is a qubit 2. We are just applying the Hadamard gate and we are just transforming the Z operation into a phase flip. Then we are just using a CCX. The CCX is nothing but the Toffoli gate. It is similar to an AND gate in a classical. This is used to apply on the controlled Z on ket of 111. So after applying this, again, I'm just going with a Hadamard gate on the second bit so that we can able to undo the phase changes. Now I'm just making a undo the first step by reapplying the X gate on the qubit 1 to make the restore of it. So this will effectively flips the sign of ket of 101 while leaving all other state unchanged. So this Groover's function will do that. So the next part of the method is known to be in a diffusion, where as we have seen on our algorithm, that we have a Groover, in a Groover's algorithm, we first step is a Groover's, that is an oracle function. The next one we comes under the diffusion, where we need to apply the inference. That is, in order to achieve the amplification, we need to work with it. So here we just used the applying the Hadamard gate. So you can able to see that I'm just trying to apply the Hadamard gate to all the qubit, and I'm just created an X gate that is going to map the ket of 101. Since I have taken the 3 qubit, I'm just considering 101 to, I'm just making it to be in a ket of 000. So this can be done with here. And I'm trying to apply within a controlled Z gate along with the Toffoli so that it applies the phase flip to 000, indirectly affecting the 101. So undo this X gate and applying the Hadamard gate again. So automatically this steps constructively interferences. That is, what is the use of interferences? Until the probability of correct solution, this need to be done, right? So until the constructively interferences with the amplitude of ket of 101, this increases the probability to get to the correct answer. Again and again, this is going to be executed because to set the 101 to 1000, that is a ket of 000, indirectly affecting the 101, again undo the X gate, and again we are just applying the Hadamard also. So this runs over and over to get to the final solution of it. And the next one is here. This is the main part of the program where we are trying to run the Groovers of it, where we have created a quantum circuit with a 3 qubit and 3 classical bit. and applying the Hadamard gate as you have seen here. So, and I'm trying to perform the groovers. So perform the 2 groovers iteration that is optimal for the 3 qubit. So applying the oracle function. So oracle function will be called, okay. And this is mark 2. Once the oracle function is called, it will be marked to cutoff 101. So after this, the function will be written over here, and the diffusion function will be called. The diffusion function will be executed, and it will be amplifies the 101 until it gets the uh, correct solution. And we finally, what we will be doing, we will be measuring of all the qubits and stimulates. And I have just given the stimulated the circuit with the help of an R simulator. So this circuit going to run in 1024 time slot, and I'm just going to print the all the solutions of it. So as of you can able to see that I have targeted the number qubit is 0 and targeted bit is 101 and number of iteration is 2. So the expected success probability is 94.5. This is because we cannot able to have the 100 because of a noise and error prone. So we have considered a 94.5, and you can able to see that this qubit, the circuit path is 22, and the operation we have finded in a 4 operation itself, it was finded. So as of, I hope that you are clear that how the Grovers was working. The 2 important part is an oracle and the next one is a diffusion, and we need to enhance the superpositions on the oracle, and in diffusion we need to be ensure the amplification. That is, amplification or the diffusion is responsible to have a probability of correct solution rather than the false solution, so that it can able to achieve the square of n solution itself. Okay, square root of n. So now I hope you are very clear about the Gruber's algorithm. So the next part we are just going to see about, we need to think about how the Grubers is executing. So I'm just skipping, as I have explained with an code lab, I'm just skipping this. So the next thing we are just going with how many qubits are needed for the Grover's algorithm. Okay, so Grover's, as we already told, that is in a quantum search algorithm, this is going to have a quadratic speedup rather than the classical brute force search. So the number of qubit required depend upon the size of the problem and the efficiency of the hardware. As we have already told, we know that we need often a logical bit to an implementation. For example, if the data is represented, that is, if the search of an unstructured database of size n we are just doing, the Gruber's algorithm requires log base 2 of n qubit to store the each search spaces. For example, if we are searching with the 1 million elements, that is n 10 to the power 6, this could be required at 20 qubits, that is a log base 10 to the power 6, that is approximately 20 bits is needed. Rather than having of entire thing, I'm just having a 1 billion element, 1 billion of operation, I can have a 20 qubit that is essential to it. So when compared to a source, this is a minimal qubit is required to perform. And you also can see in a classical, we can found that when we are working within a 1 million element, this going to have an 1 million operations, but in case of an Grubers, it's going to perform within a 20 qubits. And another one thing is we need of an ancillary qubit. That is, not only a logical qubit is needed, we also need a helper qubit in order to achieve the Gruber's algorithm. So ancillary is nothing but an additional qubit that is required to maintain the oracle and amplitude application. What we have seen, right? That is in a black box, and another thing to have a correct solution, the probability to get a correct solution. So for that, we need of an ancillary qubit that is called to be a helper qubit. This is typically around log base 2 of n, that is in a k qubit, where it is k is nothing but an ancilla qubit. That is, I have already told that you can able to compute the Gruber's algorithm with the help of a log base of n. Along with that, you need to add in a k qubit for an ancillary. So, and the next one is we need of an error corrected one. That is, as I have told already, we need of a logical qubit that will be equal to 1,000 physical qubit without a quantum error correction. So this means that for a search space, we need of a 30 logical qubit that needs of a 30 physical qubit in practices. So the groove is more feasible to run on quantum hardware when compared to an source algorithm. When we discussed on the source, we have come up with two difficulties. One is it need of more logical qubit, and also the depth of the circuit design is also complicated. But in case of when compared to with the source, Groovers is more feasible because it also needs a less logical qubit. As we have seen, we have a 30 logical qubit, and because of its lower circuit depth, we also can able to implement that much easier and feasible to work on it. So the current achievement is the Groover has experimentally demonstrated on the small scale quantum computers like an IBM, Google, and all those things. So it is successfully searched the space within a few search elements in a large scale application also. So the main Groover's challenging is error rate. That is, to do the more iteration on the square root of n, the quantum noise accumulates. So that is the main part of the research is needed. That is in order to avoid the noise accumulated. And the next one is a decoherence. That is it maybe leads to an loss of information that also need to be avoided, and the hardware limitation. We have already told that current quantum processor is available to work within a few logical bits is available, but whenever we come within a large scale of problem, that logical bits is not enough to over here. So there is a hardware limitations over there. So future possibilities is near-term application. That is, we are very, very near to it, so that the Groover's algorithm will be a most promising one to it. And we can theoretically reduce the brute force search time for the cryptographic keys. That is, it can be of 2 to the power n to 2 to the power n by 2, which means that I can able to convert the cryptographic keys to be a 2 to the power 64 instead of performing a 2 to the power 128. This also can be done because the searching, with the help of a searching, the prime factorization can be easily available. So it demonstrated in the potential world with the help of it. So with the help of an superpositions and entanglement and interference, I hope that quantum computing have revolutioning its changes, and really the source is going to be a threat to a classical cryptography, and we are just enhancing within a post cryptography research also. And this, with the help of an Groovers, we can able to have a quadratic speed up over the classical methods. So despite of considering all these hardware limitations, logical development of the logical qubit from the physical qubit, when the quantum is on the way, there will be greater simulations on security, AI, and complex simulation. So once we understood that quantum era is approaching, so once we understood it, once we prepared it for this, automatically we can able to break through the tomorrow's technology. Thank you.
Participants, if you have any doubts, you can raise your hand. Then I will unmute your mic.
Ma'am, again, Murali Bhaskaran, are you working in quantum computing, ma'am? You are doing many programs and all?
No, sir, I'm not doing. Actually, I have done the quantum challenges on IBM.
Oh, okay.
On quantum machine learning, I'm
Okay,
just,
ma'am.
and I'm
If
just.
I write a quantum program in my machine and it will run in quantum computing, how it is possible, ma'am?
Sir, as per now, we are not having that. We need to stimulate from the IBM, and I'm just using a QSKIT for that.
QSKIT, whether it will support the collab, ma'am?
Yeah. Now I have executed with the help of Colab only, sir. I have
Okay.
imported all the libraries from the QSKit and I have executed.
So QSKit is a IBM developed
Yeah, sir.
simulation.
Yeah.
It's really it is executing in quantum computing or
It's
it is
like
simulated.
no, sir. It's like in a simulators. It wasn't
Okay.
like in a simulators. It was working
Okay.
like in a simulators.
Again, it is working in conventional computer only.
Yeah, sir. Yeah. Actually,
Actually, if you
we
want to
need of
work with quantum computing, what we need to do, ma'am? Is it possible or not?
now it is not possible because it was evolving, sir. Because we need often a logical qubit.
Mm.
Since logical qubit is very minimal, so the companies like an IBM, Google is using that. So maybe in a few years it will be possible. I think so.
This two algorithm is very famous, Shor and
Yeah, sir.
Shor.
Yeah, Source and Groovers is very famous algorithm, and it is
Okay.
also in research because of Source capacity and prime factor factorizations only. The power of exponential, and it's because of time complexity only. This
Okay.
Source become more popular, and the researchers was awakened that when the logical bit on the way, automatically it will breaks an RSA, so it will be a great impact on the internet, right? So they are working on the pros cryptography and also in quantum cryptography, sir.
So whatever we do, it's a kind of simulation. It's not actually running on quantum machine.
No, sir. You can able to run like in a simulations, and you can feel the qubits and quantum and all, sir. But physically, like in a classical computer, at present you cannot able to do it. I hope few companies, I forgot that, sorry for that. Some people have come up with the quantum computer, but I don't know whether it was available on the market or I'm not sure about it.
So like array declaring array, we need to initialize the qubit also. Qubit is a data type, one data type. Huh?
No, sir. Qubit is nothing but our classical bit. For example, our classical bit is 0 and 1, right?
Yes, yes,
Yes.
yes.
As like quantum has a qubit. Quantum has a qubit in sense. It
No, no.
also
My
has a.
question is in a package in Python, if you
Mm,
declare a qubit, suppose if you have any function or any variable declaration qubit A, then
okay.
integer A, what will be the difference between qubit A and integer A? Can you, is it possible to
Integer.
define like that?
Yeah, sir. Integer A is nothing but the variable, right? But
Yeah.
qubit A, when I represent a qubit A, it represents a 0, 1, or both the state. That is, I'm just going to represent as like in a bit.
Okay.
So it's going to deal within a bit, sir. Actually, when we talk about a qubit, we can talk it to be in a 0, 1, or both the state. Both the state can be done with the help of a superposition. So when you telling int a, it marks as to be in a variable. But
Mhm.
when I mention a qubit, it will take it to be in a bit. That is mentioning of zeros and ones and also the superposition.
So these values we have to store in some other. Suppose if you qubit to conventional bit, if you are transferring, assume that.
Yeah,
So what
classical
value is it, whether it is 0 or 1 or both?
or both.
Both value if you want to store in our conventional system, we need 2 bits.
Yes, sir. Either in a
One is
conventional bit,
one qubit will be considered as a 2 conventional bit.
sir.
Am I right?
Actually, yeah, sir. Yeah. On that cases, we can able to store any of one, either 0 or 1. Is it right? But in case of qubit, we can have in a both the state.
That's what.
When
When you
yeah,
convert from qubit to conventional bit, so 1 is equal to 2 bit,
yeah, sir.
to conventional bit.
Yeah,
So if you have 2 bit value, assume that if you
yeah,
have
sir.
2 bit value, you want to store in a qubit, only 1 bit is enough. Is it possible to exchange from qubit to conventional bit to qubit? Is it possible, ma'am?
Actually, we can able to do, sir. Um so whenever the qubit is stored, you can able to store it within a classical register, sir. For example, if I'm just trying to measure the qubit, for example, 0, 1, and 2, I just go with an first thing, that is I can go with a qubit exist in the superposition that is known to be a ket of 0 and ket of 1. That is, I'm talking about a bit of 0 and bit of 1.
Okay.
When after measuring the superposition, what you have told, you can able to represent within a classical state of 0 and 1, sir. So that also can be done with the help of a classical register. We can do that, sir.
So same read print function is using, or some other function is used for writing in qubit and reading from qubit. Na?
Sir, kindly repeat your question once again, sir. I'm not clear.
No. When you work with the registers, we usually to read A, print A, like that we will use. The similar way, if you work with qubit, the same function will be useful, or q read, q write, or something like functions.
Sir, I have defined the qubit with the help of a variable called QC. So I just make my register. The register is to work with a Hadamard gate, that is to fix with a superposition and entanglement. We have used the register, sir.
Thank you, madam. Thank you very much.
Thank you. Thank you so much. Thank you, sir.
Any other questions? Yes, Siddharth, you can proceed on it.
Okay, ma'am.
There's a question in chat.
Yeah, I will.
Okay, ma'am, just came up.
Breaking discrete log. I'm not clear with the question.
Participant, will you please raise your hand, then I enable your mic.
I hope that the discrete logarithmic problem, I hope that you're asking that. For a classical computer, the discrete logarithmic will be hard. But quantum can break, I hope it will be with the help of a source algorithm. So similarly, as for the source algorithm, this is going to be as we have computed, right? A power x mod of n we have computed. Similarly, we need to compute in a function, and we need to be go with it. I hope it is in a post quantum cryptography. I'm not sure about it. I have a little bit idea about it. I hope, Jeevan, you have asked the question regarding this. I know that it will be done with the help of a source algorithm, breaking of discrete log computations with the help of source, but I need to work on that.